Yes guys, today we're going to be proving why the sine, cos and tan graph look the way they look. So the way we do this, right, is we start off with just a simple unit circle. So we have a unit circle, and obviously this unit circle, let's draw a better circle, right, has a radius 1. Let's call this 1. Now, you can see a sort of triangle has been formed here. We've got a right angle here. And let's call this angle where, sort of see this as our radius meets the origin. It's angle theta. So we just know from basic year 9 trig that sine theta is opposite over hypotenuse. So let's write up here, sine theta equals opposite over hypotenuse, and cos theta equals adjacent over hypotenuse. Now in both cases the hypotenuse is just 1, so sine theta equals just the opposite length through the angle, and cos theta is just the adjacent. Now for tan theta equals opposite over adjacent, and we know this to be sine theta and cos theta respectively. So sine theta and cos theta, and by doing this we've just proved one of the first trig identities we ever see. So that's quite nice. So let's start off by labeling sine, opposite, adjacent and whatnot. So this is 1, opposite is sine theta as we said, and our adjacent is cos theta. Now how does this help us sketch our graph? Well, it's actually very simple. So let's say we're trying to draw the sine graph. So we start off obviously at the origin. It's probably the best starting point. Let's draw it back. Sine theta. So at the origin. And when theta equals 0, so when our radius essentially is this, lies along the x-axis, our value of sine theta is just 0, because notice how we don't have any height. All we have is a width of cos theta. Well, so we have a width of 1, because we just have a width of 1 here, and a height of nothing, 0. So we start off with the origin for sine theta. Now as we increase our theta angle, we sort of form, let's make that a bit better, form a triangle there, even more triangles as we increase theta. And notice how theta is just getting larger and larger and larger and larger every time. So we need to notice what happens as theta approaches. Well, the next point of interest is really when theta is 90 here. So we're looking at the height, right? So we start at 0. Our next triangle that we form has height greater than 0, even further greater. Then we get up to sine theta equals, sine of 90, where we have a height which is equivalent to the radius from here to this point 0, 1. Therefore sine theta is 1. So from angle theta, so from theta 0 to theta 90, our sine theta value ranges from 0 to 1. So let's put 90 on the x-axis. Well, let's call this theta. And here we just call this sine theta. So let's call this 1, and we're going up to 1 like this. Now you can sort of expect something similar when we continue increasing our angle. So we were at theta equals 90. Now theta equals 91, 92, 92, up until 180. And notice how our value of sine theta returns from 1 back to 0 the same way it did. It's the same way it went from 0 to 1 here. It's going from 1 to 0. So we can see some sort of symmetry. And its theta is going towards 180. So what we do here is we take our sine theta value from 1 to 0. Now on to this next quadrant, the third one. We're going from 180 to 270. This angle here is 270. So over here, the angle is so the height here was 0. Now we're going into the minuses, so minus 0 point something up until minus 1. This is from 180 to 270, so we're going towards minus 1. Let's put that on our axis, minus 1. Again, we're getting a similar shape. Voila. Now, when we're returning back to our starting point, 0, which is also the same as 360, so 90, 180, 270, 360, we go from 270, which is minus 1, up until 0. So we're returning back to where we started, essentially. Notice how I said we return back to where we started. So if we're back at theta equals 0, then we know when we complete another rotation, so we can see this angle now as 360 plus 90, which will be 540, which is essentially, which will give us the same value as if theta was 90. So this brings about our periodic nature of our graph. We can say the same going into the negative theta values. Because of this idea of periodicity, so go back there, and 360 would have been there. So if I draw a more detailed version of the sine graph, we've got angles 90, 180, 270, 360, then we clock that, so we've noticed that this graph repeats every 360, so 360 at 360 is, let's say, 720. Between there we're just going up in 90, so 450, 540, and then 630, so on and so forth. Likewise for the negative, going from minus 90 to minus 180 to minus 270, minus 360, and again just the same repeating nature, which brings about the periodicity nature of our sine graph. Now we can again expect something similar for cos, so let's just copy this unit circle down, copy. Now notice how for the value of sine theta we were looking at the height of our triangle that we had formed. Now since we're doing cos theta, the adjacent, we were looking at the width. So again we start off with theta at 0. And as theta goes up, our width just decreases up until 90. So we started with width 1. As we go towards 90, we have width 0. So let's just sketch that. Cos theta on our y, theta on our x. So start off with 1, and go towards 90, which gives us cos 90 as 0. Now from 90 to 270, well, width of 0, width of just a bit more, sorry, not a bit more, less than 0, we're moving into the negatives, up until 180, sorry, if I said 270, minus 1. This is minus 1 from the origin. So we can say that at 180, cos theta is minus 1, and we can just expect the shape now to be similar to sine graph. So from 180 to 270, our width just keeps getting smaller and smaller and smaller up until 0. So we move from minus 1 to 0, 70. Now for 360, we're returning back to where we started. And we started at 1, so we're going from 0, getting larger and larger up until 1. 61. Now, if we look at the negative part of our graph, so we've got angle minus, from going from 0 to minus 90, well, our width goes from 1 to 0, so let's draw that on, and we just can expect the same repeating nature for every 360, 170, 360, and this graph repeats for any angle theta. That's cool. So we've drawn sine, we've drawn cos. Now what about tan? So we said tan theta equals sine theta over cos theta. So if I quickly draw on our sine graph, equally we'll draw the cos graph on top as well. We'll do the same for the negative. Now we just have to compare sine and cos. So let's work in intervals, right? I think it's wise to work in intervals of 90, 180, that should be a bit more, and that, 270, then 360. So before we start that, let's just go and let's check 0. So sine 0 is 0, cos 0 is 1, so 0 divided by 1 is simply just 0. So with the tan graph, we're starting at the origin. Now let's check when theta is 90. So we have, what do we have? We have, so let me just label our graph cos theta, and that one is sine theta. So check the black graph first. We have sine 90 is 1, then cos 90 is 0, so 1 divided by 0, and that's just undefined. So that means we have a vertical asymptote at 90. And before the asymptote, we'll have a number very close to 1 divided by something infinitely small, which just gives us a really large number. So essentially we tend towards infinity from when we approach the asymptote at 90. Now let's check between 90 and 180. So at 90, just after 90, we've got a value of approximately 1 and a number that's negatively infinitely small. So instead of starting at infinity, we start at negative infinity, because 1 over something that's negatively, let me repeat that again. We have roughly 1 here, and we have roughly 0. No, it's just negative 1 over negative 0.0001, which is 1 over a really small number is infinity. That minus makes it negative infinity, so we start at infinity and move towards 180 at 0. Why 0? Because sine 180 is 0, divide by anything will just give us 0, tan 180 is 0. Now, from 180 to 270, 180 we said was tan 180 is 0, tan 270 however, well, we've got negative 1 divided by cos 270, which is minus 1 over 0, which is undefined. So again, we just have an asymptote. Let's just draw that on. And we know that as tan approaches this asymptote, we have negative 1 essentially over a number that's very close to 0 approaching from the negative side. So negative 1 over negative 0, negatives cancel, we have infinity. Let's go towards infinity. We sort of see a pattern here. Let's just check. Well, 270 to 360. From here, we've got negative 1 over something very 0, but from the negative side. So from the positive, we've got positive there, negative here. That means we're coming from negative infinity up to a 360. And then don't even have to look at the sine and cos graphs anymore. We can just predict the shape, asymptote, and by this logic we've deduced that there's an asymptote at every 180 from 90. So this asymptote, put this asymptote 270 and then 450. Let's just check how the graph behaves on the negative. So we've got value here, so it's essentially minus 0 over 1. Well, that doesn't really help us. Minus 0 over 0.99, which is starting, what is that? Well, actually no, let's just not evaluate it, let's evaluate at minus 90. Well, minus 1 over 0, which gives us a asymptote at minus 90. And before the asymptote, we have a number that's essentially negative 1 over a number that's really close to 0. So that's again negatively infinitely large. So again, just the same pattern, and we can repeat this same pattern. Minus 270, so on and so forth. And that is how we derive the tan graph. That's all for the trig graph. Hope that was informative, and see you in some more proof videos. Goodbye.